Hi guys, today we're going to start chapter 5. We're going to start off with section 5.2, which is called one-to-one functions and inverse functions. The first thing is we're going to talk about one-to-one functions. A function is one-to-one if any two different inputs always give you two different outputs. So for example, this mapping right here, this would be a one-to-one function. Every x gets one unique y that it's paired up with. So this is 1 to 1. This over here, this is a function. These are the functions we've dealt with before where it's okay for two x's to have the same y value. This is still a function, it's just not a one-to-one function. Whereas this one over here, this is not a function. So if one x splits to two y's, that's not a function. This is a function, this one's okay, but these are the functions we're going to be talking about today, which are one-to-one functions. Now, there's a lot of different ways that you can tell whether a function is one-to-one. One, if you're looking at a graph, the graph of a one-to-one function will pass what's called a horizontal line test. So this right here is an example of a function. You can tell it's going to pass a vertical line test, but this graph fails what would be called a horizontal line test. So if you can draw a horizontal line and you hit your graph twice, that's not a one-to-one function because these two different x values both have the same y value. So that would be a situation kind of like this mapping right here. So that would not be a one-to-one. So a one-to-one function will pass a horizontal line test, which I'll show you an example of here in a second. Looking at a mapping, it's pretty obvious if something's one-to-one. So this mapping right here, this would be a one-to-one function. Every state gets matched with a population over here. So that's one-to-one. This is not a one-to-one function. Still a function, it's just not a one-to-one function. So yes, this is, no, this is not. Okay, dogs and cats have similar life expectancy. Apparently ducks, lions, and pigs do as well. So anyway, this is not a one-to-one function. Looking at these two graphs over here, this is a one-to-one function. Okay, every time I draw a horizontal line, I'm hitting my graph in one spot only. So every x gets a unique y that it gets matched up with. This would not be a one-to-one. If you draw any horizontal line, you're going to hit that graph in multiple locations. So all of these x values have the same y value. So that's not a one-to-one function. When you're looking at ordered pairs, you need to make sure the x's don't repeat. That'll make it a function. But you also have to make sure the y's don't repeat now. So every x has to have a unique y. So this one would be, yes, that is a one-to-one function. The reason we are concerned with whether or not a function is one-to-one, if a function is one-to-one, then it has an inverse. An inverse function will undo the original function. So for example, I've got a couple functions right here. For this function, I'm going to put a 10 into the function. I'm going to do that math. So 8 times 10 is 80 plus 5, and I'm going to get 85 as an answer. That 85, if you put that 85 into this function, well, 85 minus 5 would be 80, and then 80 divided by 8 would be 10. So this function undoes what this function does. For this function, you put it in 10, you get 85 as an answer. For this function, you put it in 85, and you get back the 10 that you originally had. So this function is an inverse of this function. We have a symbol for that. This is the symbol for an inverse. So if f of x is this function, 8x plus 5, then the inverse of f of x would be x minus 5 divided by 8. Okay, so that's an inverse symbol. Now, if you notice on that original mapping, okay, notice that f of x has an input value of 10 and an output of 85. But for the inverse, it was the opposite. We put in the 85 and we got an output of 10. So this is the domain and this is a range value for the original function, but those two flip when you're looking at an inverse. And that's what this next part talks about. It just says that the domain of a function is equal to the range of its inverse. So that's going to be important here in a second. So the domain of a function is equal to the range of the inverse, and the range of a function will be equal to the domain of an inverse. So if I have a function that has a domain of all real numbers, its inverse will have a range of all real numbers. And if I have a function that has a domain of just, let's say, x greater than 0, then the range of its inverse will be y greater than 0. Okay, they're going to be equal to each other. Down here, if you look at these examples, okay, finding the inverse. So this is a one-to-one function. Dan drives a Saturn, John drives a Pontiac, Michelle drives a Honda. The inverse would be the opposite direction. So you tell me the car, so whether it's a Saturn, a Pontiac, or a Honda, and then I'll tell you the student who owns that car. So that's what this function would do. So the Saturn, that's Dan's, Pontiac, John, and the Honda, that's Michelle. Okay, so that's it. You take the domain and you turn it into the range, and you take the range, you turn it into the domain. Okay, for ordered pairs, you literally flip the x and the y. So for this, it would be 5, 1, 8, 2, 11, 3, and 14, 4. So that would be the inverse. And you can see that the domain of the original was 1, 2, 3, and 4, but that's the range of the inverse, 1, 2, 3, and 4. Okay, so the domain of the original is the range of the inverse, and the range, 5, 8, 11, and 14, have now become the domain of the inverse function. Okay, so this is the inverse, the domain, 5, 8, 11, 14, and the range would be the 1, 2, 3, and 4. Okay, state the domain and range of the inverse. So there's the domain and there's the range of the inverse. All right, so since a function and its domain, a function and its inverse, you literally just switch the domain and range, then the graphs of a function, here's f of x, the graph of a function and the graph of the inverse function are going to be symmetric across the line y equals x, because that's literally what we're doing. We're taking the x's from one and we're making them the y's of the other, and we're taking the y's of one and the x's of the other. So these two are gonna equal each other. So for example, if I have the point a1, b1 on my function, then the inverse would have those two switched around, b1, a1. So think of actual numbers. So if this is -3 and then down 1, so -3, -1, the inverse function will have -1, -3. So you literally just take the x and the y and you switch them, and so those are going to be points that are symmetric across the line y equals x. So if you're given a graph and you're asked to draw the inverse, one thing to do would be to write down these points. So this is -1, 0. This would be 0, 3. And then this would be over 1 up 4, so 1, 4. And you take those points and you just flip them. So the inverse is going to have the point 0, -1, which is right here. 0, -1. It's going to have the point 3, 0, so 1, 2, 3, 0. And then instead of 1, 4, it's going to have 4, 1. So you'd go over 1, 2, 3, approximate. That looks like 4. And then up 1. So that would be the point 4, 1. And if we connect those dots, that would be the graph of the inverse of that. So any graph I could give you, that's all you do. Find the points and then just switch them, and that'll be the graph of the inverse. Okay? And this graph is symmetric to this graph across that line, y equals x. All right, for our last section, we're going to take a function and we're actually going to find the inverse of this function. We're going to find another function that would do the exact opposite. that this function does. So the first thing, so you've got the steps right here. The first thing you want to do is you want to replace the f of x symbol with y. So we want to write this more like it's an equation. Okay? Next step is to switch the x and the y. So the inverse and the domain have the x's and y's switched. So if we just take the x and y and switch it, so x equals negative 1/3 y plus 1, this is actually the inverse of that. Now, we don't want to leave it in this form. We want to solve for y. So we're going to move the 1 to the other side. And then we would multiply both sides by, since this is being multiplied by negative 1/3, we'd want to multiply by a negative 3. That'll cancel out the negative 1/3. But we'd have to do that on both sides. And we would have to distribute over here. Plus 3 equals, these will cancel, giving us y. And now we can substitute back into the function notation. But this is the inverse. So it's the inverse function. And it's equal to negative 3x plus 3. Now, if you look at the directions, it also says we're supposed to find the domain and the range of each. So we want to find the domain and the range of the original function, and we want to find the domain and the range of the inverse function. Well, what we're really going to do is we're just going to find the domain of both of these, because we've done that before. To find the domain of a function, you just need to make sure there's no x's in the denominator that could give you a 0, and there's no like square roots, something that you can't take the square root of a negative, that sort of thing. So for this one, we don't have either of those situations, so the domain is all real numbers. If you look at this function, also, we don't have anything going on with that, so that would be all real numbers. And the reason we only need to find these two things is because the domain of the original is the same as the range of our inverse function. So if this is all real numbers, this is all real numbers, and vice versa. The domain of this is the range of this. So the domain and range of both of those, the original and the inverse, would be all real numbers. Okay, the second example. Now, check this. Some of the notes had a typo. This should be 3x cubed, not squared. Okay, so make sure that says cubed. All right, same thing. We're going to rewrite this as y, and then we're going to switch the x and the y. So some of you may just want to do this in one step. So x equals 3y cubed plus 2. Okay, so I rewrote it using x's and y's, and then I flipped the x and the y. Now we want to solve this for y. So we're going to move the 2 to the other side. Oh, excuse me. Minus 2 equals 3y cubed. We're going to divide by 3. X minus 2 divided by 3 equals y cubed. And now we would just take the cube root of both sides. Cube root x minus 2 over 3 equals y. Okay, so that is our inverse function, so we can rewrite it using the inverse notation. And this is the inverse function of this. Okay, and you can kind of see the connection. You can see a plus 2 and a minus 2. We're multiplying by 3, we're dividing by 3. We're cubing, we're taking the cube root. So you kind of see the inverse operations that are there as well. As far as the domain and range, again, domain and range, domain and range. We're just going to find the domain. Well, this would be all real numbers. The domain of this cube root, you can take the cube root of a negative. So there's no restrictions on this one either. So the domain would be all real numbers. And then again, the domain of this is the range of this one, and the domain of this is the range of this one. Okay? All right, last example. Now, this one is definitely something that you're going to have to pay attention to. So, this one I am going to do in 2 steps. I'm going to rewrite the f of x as y. Okay? Now I'm going to switch the x's and the y's. So this y is now an x, and both of these x's are now y's. So here's our issue. I've got two y's, and I need to solve for y. So I need to have one y eventually. So the first thing, whenever you have a variable in a denominator you want to solve for, you want to cross multiply to get rid of that variable in the denominator. So cross multiply. This y minus 1 is going to multiply that x. So I'm going to distribute xy minus x equals 2y. Now the trick is get the variables on the same side. So I'm going to move my y's over here. You can move the xy over here. I just like to have my y's on the left for some reason. Okay, so I'm going to take the 2y, subtract it over here to get it next to his buddy. And I'm going to take the minus x that doesn't have a y, I'm going to move him to the other side. The reason we do that is because now these two y's are a common factor that I can factor out. And then I can just divide by the x minus 2. And this is the inverse function of that. So, inverse function x over x minus 2. Okay, now, for the domain and range on these, domain and range, this one we've got some fractions, so we are going to have restrictions. Okay, the domain of this, x cannot equal 1. But if x cannot equal 1 is the domain restriction on this, then we're going to have a range restriction over here. Y cannot equal 1. Now, knowing what you know about horizontal asymptotes, if you look, this is an x over an x, so this would have a horizontal asymptote at y equals 1. And that's why this is going to have a range restriction there. For this one, your domain would be x cannot equal 2. And again, that means on the original function, the range will have y cannot equal 2. Okay? So that's the function, that's the inverse, and that's the domain and range of each.